All right, so now let's start practicing the various methods that we just learned with exponents, okay? Solving exponential and logarithmic functions. All right, so let's go ahead and begin. The first one, it says, what is the solution to the following log function, or that log equation? And it says solve using both the exponents and the graph. So real quick, the exponents right here has to do with what we've learned before as the reverse Hart method. And that's just a rewrite from logarithmic to exponential. But it goes hand in hand with something that we just learned, which was that same base kind of formula. So same base, if you will. And again, this is without a calculator. And then we'll use a graph. Okay, we'll use a calculator to do it another method. And at the very end, I'll just use the solve feature as a last, not a first, resort as far as just to see, did we get the answers correct? All right, so let's go to begin. So we know that the common base is 10. So it's log base 10 of the argument 3 minus 2x. And this reverse Hart method says I can rewrite this as an exponential function. Okay, and it's going to be 10 to the power of -1. And it's equal to the second part of this reverse Hart method. It's equal to the argument, which is 3 minus 2x. Okay, so now this reverse Hart method goes hand in hand with the same base because here, I mean, we could try to get the same base, but for this particular problem, we're not going to be able to. Therefore, we're going to have to solve it out fully as far as without a calculator of what would x equal in this respect. Okay, so we know 10 to the power of -1 is the same as 1 over 10 to the power of +1. Okay, and that's just understanding that there is a denominator of 1 right here. And this negative power, we've talked about this before, makes the base move to the bottom, the denominator. And when it does that, it changes that base to a positive instead of the negative that it was. Now, look at that 1 up top. This is an understood one that has always existed in the numerator, okay? Please do not confuse this as, oh, we just took the reciprocal, okay? This one, because this one could sometimes be 2, it could be 30, it could be different numbers. It doesn't mean that that number jumps to the numerator. So careful with that. Okay, so we have 1/10 is equal to 3 minus 2x. Okay, and from here, we can go ahead and move stuff around. We can add the 2x to the left side. I like to have that coefficient of x positive. And we could leave the 3 here and end up subtracting the 1/10. Now, there's many ways to do this. And you might see the handwritten key might be just a little bit different. But nonetheless, our goal is to get a positive x to be all by itself. Okay, so when I'm subtracting this 3 minus this fraction, we're going to get a common denominator because right now the denominator is 1 for 3. We're going to multiply by a form of 1, which is 10 over 10. Okay, this is a form of 1. So that we get 30 over 10 minus 1/10 is equal to 2x. Okay, so we have 29 over 10 is equal to 2x. And when I'm dividing by 2, it's the same as multiplying by 1/2. Okay, so dividing by 2 is the same as multiplying by 1/2. And I'm going to put dividing by 2 here. But then since it's dividing by 2, this would look weird. So I'm going to say multiplies by 1/2. So that I know that this or these denominators are going to multiply together. They don't have to be common when I'm multiplying. Just adding and subtracting, they do. So we get 29 over 20. So 29 over 20 is going to be the answer for x. Okay, without a calculator, fully, a lot of algebra going on and manipulations of some sort, but nonetheless, I got it without a calculator. Now, if I did it with a graph, let's go to the graphing calculator. And I on purpose left this here because between problems, I want you to press delete 3 times. And before we do that, we have to press Control T to get rid of the table. Then we'll press delete 3 times. Press yes because we want to delete everything. And then menu, window, standard. So menu 4, 5, and you're back to normal, okay? So you don't necessarily have to clear the calculator fully in between problems like home to menu C, okay, okay, and stuff like that. You can do it just the way I did it here. Now, remember, when we did the graphing method, we need the left side to be a function and the right side to be a function. This common base of 10, notice how I will not have to input it, but that it will still register as that common base. So log of 3 minus 2x is what I'm inputting my left side for f of 1. And notice that it automatically threw in that 10 because it's an understood common base, the common base, okay? So now when I come over here, I'm going to put the right side of the equation, which is a -1. This is my second function. Okay? And now all I want to see is when are these two graphs equal? So I'll say menu, and you notice we did not have to zoom, we didn't have to edit the window. This one was a lot easier than the example problem that we worked out on the other video. But again, they're not always going to be this easy. So we'll analyze the graph, we'll do the intersection, the left bound, drag to the right, and sure enough, there's my answer. 1.45 is going to be that answer. Now you're probably asking yourself, what is 1.45? Well, remember on the other one, we got 29 divided by 20. So we have 29 over 20. And if I press Control Enter, I'll get the decimal equivalent, which is 1.45, which is the same as what this is. So they're both the same answer. They're both going to be 29 over 20. And you can put it even over here, or this answer of 1.45. X equals 1.45. And yes, with the graphing calculator, just to save time, you would graph these as far as where they would go in the function. And this one looks like it's going to approach an asymptote. Just real quick, just for FYI, this asymptote is going to show you where, in fact, this would equal 0. So 3 minus 2x is equal to 0. And the reason why I'm setting it equal to 0 is that's the original vertical asymptote of a logarithmic function. Okay, so we're trying to see, did it shift? Did it move? You know what I mean? As far as what was the x value changed to show our new vertical asymptote. So we'll say 2x is equal to 3. Therefore, x is equal to 1.5 or 3/2. So at 1.5 or 3/2, right here, this is where that function is going to have a vertical asymptote. Okay, so let me go ahead and draw that vertical asymptote right here at 1.5. Okay, and yes, I'm just doing a quick sketch. Our first function was that log. It looks something, whoops, it looks something like this. Whoa, and it doesn't show necessarily. Let me try that again. Something like that. And that's just a rough sketch. And it doesn't show like the vertical asymptote. The graph will not show that because the graph only shows where it's defined. And here it doesn't show that it will infinitely get closer to 1.5. This is the way the graph is interpreting and showing us that that is what's happening. Okay. And then the other function that we had was a -1. And sure enough, the -1 would come down here. And where they would actually exist as far as crossing each other or touching would be at 1.45, which looks like it's right there. Okay, so there's just a quick sketch. I just wanted to show you the big reason why I did that was primarily just to show you that x is equal to 1.5 was the new vertical asymptote. Okay, and that's that argument piece from my original logarithmic function set equal to 0 and solve for x. That will show you where it shifted and where it moved to. Okay. All right. So next question. It says, would a sustainable, renewable natural resource when you manage forests properly? Your lumber company has 1,200,000 trees. You plan to harvest 7% of the trees each year. How many years will it take to harvest half the trees? Okay, so this is going to have as far as like a rate and a principal, and it's going to use our function that we've seen before of a is equal to the principal 1 minus instead of plus, and it's going to be r, and it's going to be raised to the power t. So this isn't compound interest. That's not what this is. It doesn't have an n here and an n down here because we're not talking about the number of months. This is strictly as far as years and how many year increments that it's going to have. Okay, so it's not necessarily compound. And if you don't see the word compound, you're going to just think of it almost like simple interest, not the compound interest. Okay, so we know that the interest rate, if you will, is going to be 0.07. So as we're building this equation, we know that we start with 1,200,000 trees. So that's our principal amount. Okay, so our interest is 0.07, our principal is 1.2 million, and then our time is what we want to find. This is our unknown. We don't know how many years that it will take. Okay, that's our unknown. But here's the thing, it says half the trees, to harvest half the trees. So if we want to harvest half the trees, then we're going to end up with half of what we started with. Okay, so half of that 1.2 million, it will end up becoming 600,000. And that's the amount that we're going to set over here as far as the result amount. Okay, so the result is going to be half the trees. So I'm going to set that to 600,000. And then we're going to have 1.2 million. And it's going to be 1 minus 0.07. Okay. And you could write that as 1 minus 0.07, or you could just write 0.93 if you wanted to. And we're going to raise it to the power of t. Our goal is to solve this right here, okay? Now, we're not told how to find this right now. We're not told use graph, use table. So you could use whatever method that you want. But something that I want to show you right now is very, very important, is that there's multiplication right here, okay? The biggest mistake people make right there is they take 1.2 million and they'll say 1,200,000 and they will multiply it with 0.93 and they get this number here. I want to show you right here, because of PEMDAS, exponents are done first and then multiplication. So this is multiplied with this. So with that being said, when you have this power here, you cannot multiply these two together. You cannot multiply those two together to get 1,600. So please do not combine these two together, again, to 111,000 or 1,116,000. Do not do that. That is a common mistake, but please don't go there. Our goal is to break up this multiplication. Because again, we want a base raised to a power is equal to a number, okay? So when I divide both sides by 1.2 million, these cancel to 1, and this becomes 1/2. Now, you've probably heard this in chemistry, if you've already taken chemistry, something like half-life. And it wants to know how many years does it take for something to achieve its half-life. And all that's saying is how many years does it take to cut whatever you start with in half, and that's it. So this is not a coincidence. This half is going to be equal to 0.93 raised to the power of t. That's what this half-life is referring to, okay? And notice the setup, how we did it, how we started with 1.2 and what we were wanting to end with. That shows that it's going to end as half of what it started. So now we just have to find what is the power as far as that makes this equal. Now you have a decimal base, okay, and you don't know any numbers that are in common between these two. So this is not going to be a non-calculator kind of easy algebraic manipulation. We're going to have to use the calculator for this one, okay? So we're going to practice as far as with the calculator, we could do it by a graph, or we could do it by like a table, or we could just simply try to rewrite this as a logarithmic function, because right now this is exponential. And the best way to, in my opinion, the best way to solve an exponential is to rewrite as a log. So rewrite it as a logarithm. And vice versa, if you had a log, you've noticed by now that the best way to solve a log is to rewrite it as an exponential. Okay, so let's rewrite this as a logarithm. The base is 0.93, so log base 0.93. And the argument is going to be this thing over here, 1/2. And it's equal to the power, okay? And the reason why I know that is because I could, if I wanted to, do the reverse Hart method from here just to check, did I do this right, okay? So 0.93 raised to the power of t, well, that's here. And then you would say is equal to 1/2. Well, sure enough, I did. I got it right. So now all I have to do is put this into my calculator and I have t, okay? So let's go to the calculator. We're going to go to log base of 0.93, and we're going to say the argument is 1/2. Control enter, and there is my answer. It's approximately, again, 3 decimal places, 9.551. Okay, so we're going to come over here and say t, is approximately, so we'll do that as better squiggles, 9.551 years. All right, so again, 3 decimal places, that's a good default unless you're told otherwise in the problem specifically. And yes, as far as just to check it, for the sake of time, I'm not going to show you the graphing or a table. I'm just going to show you the solve feature, okay? So my initial thing that we had was 600,000 is equal to this stuff here. And if I did that as a solve feature, I could say menu 3.1. Again, this is just to check our work. This is not to replace our work. So really hope that you're not doing that because you're hurting yourself in the long run big time if you don't learn the manipulation, algebra manipulations that we're doing here. Please, please do not just use the solve feature. And then we're going to say times this 0.93 raised to the power of t. You could say x. And then do comma, whatever variable it is, control enter, and you get 9.551. Okay, that's just a check just to make sure that we did it correctly. All right, so let's move on. Next question says, wood is sustainable, renewable natural resources. We have 1.2. It says, how many years will it take if you harvest 5% instead of 7%? Okay, so we're just trying to find the difference here, okay? So it's the same setup because we're trying to take half of the trees. So we start with 1.2 million. We are going to harvest. Harvest means to gather, to remove. So it's going to be subtracting. So it's that 1 minus the r to the power of t. And since r is 5%, we know that 5% is the same as 0.05 in decimal form. So it's 0.05. And yes, you could have written just the 0.095 or 0.95, that is. You don't have to write it like this. You could write it like this too. But nonetheless, it will result in half. So it will result with 600,000 here and 600,000 here. Again, I know you could just menu solve feature that, but we're trying to develop other pieces of our math. So we're going to divide by 1.2 million, both sides by 1.2 million. So it becomes 1/2 is equal to the 0.95 raised to the power of t. Okay. For more practice, this is an exponential. So the best way to solve an exponential is to rewrite it as a logarithmic. So the base is 0.95. This is the argument. And the power is over here all by itself because it, again, reinforces the reverse Hart method that would rewrite it back to the exponential form. Okay, so it does, in fact, check out. 0.95 raised to the power of t is equal to that. So now I'm going to go ahead and put this into my calculator, and that is my t. Okay, so let's come over here, and we're going to say the log base 5. Again, I don't want you just to learn the solve feature. I don't want you to learn just one way of doing stuff because it will hinder your learning big time of the various ways that you could be asked on other tests like the SAT, ACT, and so on and so forth. AP testing, all kinds of other stuff. Okay, so we have 13.513 is the time. So t is 13.5 13 years. So obviously, this one was 13.5, and this one over here was 9. So this one did take longer, which made sense because we were only harvesting 5% rather than the 7% each year. Okay? And yes, for the solve feature, you could go ahead and put this into your calculator as the solve feature of all of that, comma t, and it would still spit out the answer 13.513. Let's keep going. What is the solution to the following? Our goal is to find x. Okay, so a good default, like I've already been doing already, is we want to try to start all of these questions, all of these exponential and logarithm questions without a calculator. We're going to use laws of logs and trying to condense this to find what is x, okay? So the first thing that you should notice is that they're both bases of 10, common base. And because they are the same, when there is a subtraction, it's the same as combining these into one equation that looks like this. I will take this 6 and I will divide it by 3x. And the reason why I'm dividing is because this was a subtraction between two logarithmic terms. So I'm going to take this 6 and it will be divided by this argument. Order does matter. It was subtracting 3x, that's why it's on the bottom, not on the top. Okay, and this is equal to a -2. So all I did, I used one of the laws of logs. Okay, now from here, I'm going to try, well, I notice a logarithmic function, so I'm going to try to rewrite it by using the reverse Hart method or the same base. Okay, we learned the same base today, that we could apply a base of 10 here and a base of 10 here. So this is another way that you can cancel this out to make this kind of come downstairs. Okay, so if you see that you can apply log, okay, we did this before. Let me show you. If I have 10 raised to the power of x and I wanted to cancel, let's say that I said that this was 1. I wanted to cancel this 10. You saw on the previous video that you could apply a log base 10. And these would cancel and you would have x. And what you do to one side, you must do to the other. So you would have something that looks like this. Okay? That's when I started in exponential form. If I start in logarithmic form, I need to apply a base of 10. Okay? So it's a little bit like this. The only difference is that this is going to be a base and this will be a base. And these original pieces became powers, okay? So this log base 10 and this 10 will cancel, and this 6 over 3x comes down. And then I have it, 6 over 3x is equal to 10 to the power of -2. If you don't see that, which a lot of people don't, this is why we encourage that you just use, whenever you have a logarithmic function like this or an equation, just do the reverse Hart method and write it as 10 to the power of -2 is equal to this argument right here. Which, guys, this is exactly what we were just showing just moments ago. Okay, yes, it was backwards. It was the 6 was over here and the 10 to the -2, but nonetheless, it's the same thing. So now you can finish it off by now solving for x. Okay, so 10 to the -2 is the same as 1 over 10 squared, because you just moved it down into the denominator. And you have this. Well, we know that 10 squared is 100, so we could rewrite this as 100. And now we have a fraction that we're just solving for x. So back in geometry, where we did cross multiplication, we could do that. 1 times 3x is 3x. And then that was just these two multiplied. And then 100 times 6 is 600. So that x is going to be divided by 3 to get 200 right here. So the answer to x with this one is going to be 200. Notice how we did this as far as we could have done the reverse Hart method, or we could have done the same base, okay? And I'll show that same base here one more time. We wanted the basis to be the same here. Okay, so to cancel this log base 10, I applied. So if it was log base 8, I would apply a base of 8. If it was log base 6, I would apply Like if this was 6, I would apply a base of 6 to both sides. So whatever that number is, we're going to apply the base to both sides, okay? So this is a 10. I'll apply a base 10 to both sides, and this cancels out, and it's left with 6 over 3x. And on this side, it's just 10 to the negative 2. And again, that's the same as here, which is the same as what we did. The most difficult part, I would say, is that not everyone's going to do it exactly the same. There's going to be many, many different forms and many different ways people will solve these, but nonetheless, you should get the same answer. And again, the focus is to do it without a calculator so that you can refine all of these algebraic manipulation skills. Let's check it simply by plugging in the original problem and seeing what is x. Okay, so here we go. I'm going to plug in, here we go, menu 3.1, and it's going to be log of 6 minus the log of 3x is equal to negative 2. And for me, calculator, can you please solve for x? And sure enough, x is 200, just like we got. All right, last page of notes. The enrollment in a private school was initially, so already I'm thinking my principal is 120, and has been increasing, so I'm thinking adding by 30%. So I'm already thinking this for my 1 plus or minus my rate each year. Formulate a logarithmic function, t of x, that approximates the number of years t it will take before the enrollment reaches x. Okay? So here we go. This is a growth problem because we saw this was adding. So our equation is going to be a is equal to p 1 plus r to the power of t. Now, if I simply replace the things that, as I was reading, are the interest rate, or not the interest rate, but the rate of increase or decrease, or the principal amount, I'm basically trying to see what is my equation going to look like. Okay, so let's go ahead and put a, is 120, and we have 1 plus 0.30, and it's raised to the power of t. Now, here's an important piece right here, okay? It says formulate a logarithmic function t of x that approximates the number of years t it will take before the enrollment reaches x. So if we're trying to see when does this reach x students, let me highlight that. Remember, you start with p. This is where you start. Let me write that right here. You start with p. The a over here is where you end up. So you start and you end. Well, they're saying that it reaches x students. So they're trying to confuse you just a little bit with variables. We want it just to become x. Okay? And our goal right now is to create a t of x function. Basically, just solve for t. Okay? So if we're trying to get t all by itself, we have to know algebraic manipulation. Like I could put, and real quick, I'm just going to show you, I could try to solve this function for t, and look what it does. So menu 3.1, we could say this function right here, the way you see it with x is equal to, 120. Make sure you put multiplication between parentheses because it doesn't always think that they're parentheses as far as multiplication. Raised to the power of t, and we're telling the calculator solve for t. And we get this ugly answer. So this is why I don't want you getting used to the calculator, because it doesn't necessarily make sense per se in a lot of regard. Okay, this is not the answer that we're looking for. We're looking for you to do by hand without a calculator algebraic manipulations that will get us to get t all by itself. All right, so let's simplify some stuff. We have 1.3, so we have 120, 1.3 raised to the power of t is equal to x. Our goal is to get t by itself because that's what we were told to find. And now we can, from our algebra skills that we've learned thus far, divide by 120. And now, how do we get rid of a base of 1.3? Well, we're going to apply a log with a base of 1.3 to both sides. So log of base 1.3 of this argument. Okay, notice that these will cancel and t will be left. And when you do the same on the left side, you're going to say the log base 1.3 of this. So t is equal to log base 1.3 of x over 120. So since we got t all by itself, this is the answer. So we'll just say t of x is equal to log base 1.3 of x over 120. And now it's a function as far as x goes, because now we can put any input here as far as where x goes, and it will tell us the time that it took. The number of years over here approximates the number of years t it will take before the enrollment reaches this specific x value. Okay, so it definitely requires by hand without a calculator algebraic manipulations in order to solve those pieces. Okay, so our last problem. It says the function t of x is approximately, or is this right here, approximates the number of years t required to reach an enrollment of x students at a private school. About how many years will it take for the enrollment to reach 500? So we want the x, we have to read it very carefully, an enrollment of x students. So if we're wanting it to reach 500 students, then x equals 500. Okay, not t of x is equal to 500. So a common mistake here would be people would take this 500 and they'll put it right here and solve backwards for x. But that's not what's happening here. It's just a clever question disguised of showing you that you have to understand what x is representing. X is representing the students themselves, okay? And that x is going to be 500. So that goes right here. And it says, how many years will it take for the enrollment to reach that? So this will say it will take t years in order to reach, x would be right here as 500, to reach 500 students. Okay, so simply we're just going to put this value of 500 inside. So we'll have log of 500 minus the log of 120, and it's over the log of 1.3. Okay, now we're going to see what is that t. So t of x, otherwise just t. How many years will it take? Okay, and yes, if you put t of x, you're really supposed to put t of 500, but I don't want it to confuse you because we're just solving for t. I don't want you to think, oh, this is t times 500. No, no, no. This is like f of x, okay? So we want it to be just t. Now, if, like I said before, we're going to default, try to solve something by hand without a calculator. Let's see what we get. We have 500 minus 120. So that's 500 divided by 120 with the same log. And it's over a log of 1.3. Okay? This is t. Now, if I was looking at this and I wanted to solve this as far as, could I even combine this even more together? Okay? So log of something divided by log of something, there's, as far as manipulation, we're not going to put this into a subtraction problem, okay? Our goal is to see, can we try to combine this all together in one logarithm to solve for t, okay? And for this one, it's difficult. We actually can't do these numbers primarily because this decimal is here. But if I were to go to my calculator, I know that I could put this into my calculator and it would give me the answer for t. Or I could even do a change of base formula. Okay, we've done this before. Remember when it was log base a of b was the same as log b over log a. Change of base formula. Okay, there were a couple videos a couple days back. So this could also be written as, well, down here is just the base. So if I wanted to combine it all as one, I could say the log base 1.3 of what I have up top. So all of this is the original argument that was up here, okay? That you could rewrite it as 500 over 120. I need you to see the equivalence and all these properties and formulas that we talked about throughout this unit to see, because things can be given to you in different ways, in different forms, and we have to interpret going back and forth between those forms. Okay, so let's put this one into the calculator first. So we have a big O division of log of 500 over 120 and log of 1.3. So our answer would be 5.439. And 5.439 is going to be over here, we're going to say years. And that's one way that we could solve it. We could have also put this into the calculator, and notice that we're not going to be able to get this decimal without a calculator, okay? But nonetheless, we practiced pieces of rewriting without a calculator. Okay, so log base 1.3 of that. Let's see what we get for that. Log, oops, I need the base, so I'm going to find the log here. So log base 1.3 of, let's see if this rewrite is equivalent to this original piece. And again, this was change of base formula. So 500 over 120. And sure enough, you see that it is exactly. Okay, so those are practice with solving exponential and logarithmic functions, primarily without a calculator, and then if not, finish it up, leaving the solve feature as your very, very last resort.